Okay, last time then we looked at modelling a structure, and we chose a structure that most people are familiar with, a bench seat, typical park bench type arrangement. We talked about the fact that there were various loads, and we'll talk a bit about modelling now. Okay, last time, if you remember, we only talked about the load that it had to carry, which was somebody sitting on this seat, and that had we said that action had various reactions at these locations here, and we called those R1, R2, R3 and R4. And we said that all the forces or actions in the vertical direction had to add up to 0, and because this was negative and these all added up to being positive, we took positive in the upwards direction, that this structure was or we needed to check that this structure was in equilibrium, so such that if the ground was too soft, for example, and couldn't produce these full reactions, then there would be a tendency under Newton's laws where force, or the action, which is a force, is equal to mass times acceleration. So if there's an imbalance, if there's a net force in any direction, so if the sum of all the forces does not equal 0, and we said forces, and we gave them actions, F for actions and subscript V for in the vertical axis. So the sum of all those had to add up to 0 for this to be in static equilibrium. If they didn't add up to 0, then we would have some out of balance action, and that would give rise to an acceleration of this bench, which has some mass. Okay. And what would happen in that situation is if this force was too great for the ground to be able to react it, if the ground was too soft, then the ground is essentially has some variation in the force that it can react with depending on its compression. And again, we can model the materials, and we'll come and talk about the model of the materials, and we can model those as springs, and we can model those as linear springs. So we can assume that the ground, which it doesn't, and we'll come on to that, but we can assume, for the purposes of a simplified model, that those springs are linear elastic springs, and as this sinks down, the ground gets compressed more and then produces a greater reaction until we reach an equilibrium point where all the forces in the downward direction are reacted by the compressed ground reacting in the upwards positive direction. And although the bench may sink a few inches into the ground, it will reach a point at which equilibrium is restored. And we said that for vertical equilibrium, all our actions needed to sum up to 0 for that to be in static equilibrium. So talking about models, we've already talked about modelling, how we model the springs in the soil and how we might simplify the reality for the purposes of doing our analysis. The art of modelling a structure is to come up with a structure which is simple enough for our purposes, but sufficiently detailed enough to give us sensible, useful results. So we could, if we're analysing the global aspects of this structure, the global stability of this structure for sinking or sliding or overturning, then we can simplify the model to the components that we need to discuss. Now, in reality, this bench is made up of the legs, and those legs have a connection to typically a downstand beam, which connects those two legs and picks up components in this direction, which are the bench planks, or the planks which make up the seat of this bench. Okay, but that's more complicated than we need for the global equilibrium checks that we're interested in doing at the moment. So, and in fact, we can dispense with the entire detail, if you like, of the structure and just consider it to be some maths, and we can consider the solid mechanics of that solid mass, which we've assumed is, or we're just modeling it as a cuboid in this instance. And similarly, the forces or the actions that we're considering, whereby we did have a system of forces meeting reactions, and those reactions were 4 in number at each of the legs. We can dispense with those reactions, and we can just bring those back to a sum. So the sum of all the reactions, and just call those a reaction generally. So they add up to some reaction which is balancing this action here, F. And for equilibrium, we can generate an equation, and we can say that the sum of all the actions in the vertical direction have to add up to 0. In order that we can consider other directions, we need to come up with some system of coordinates. And for the purposes of this exercise, we will come up with a system of coordinates which you may have come across if you've studied maths. So we have a direction which we will call the y direction. A direction, I'll draw this in isometric view, same as I've drawn the model of our structure. So we have a direction which we call the x direction, and then using a right hand rule, so if we take our right hand and if we look at it in the direction of our structure here, we will call this the x, this the y, and this the z. So we've got x, y, and z comes out towards us, and that's just a convention. And we will adopt that convention. Convention comes from, well, originally from a Latin word, convenio, I think it is, which just means to come together. So basically, convention means a convenient way. So that's where people come together with an agreed way of talking about things. And that's all a convention is, and there are different conventions. And we will talk about some of those different conventions. So we won't use this system, for example, when we are talking about the cross-section of a steel beam, for example. We might use different coordinate systems. But for now, we're going to use y in this upwards direction here, which is the direction we've got the forces acting in here. So x along here, and that represents this plane here, which is this plane here in our coordinate system, and we will give this direction, we'll call that z, and it will be positive in that sense, so coming along in this direction here. Okay, so any force in any direction, some random action, and it might be F, and we'll give it a subscript D for our design action. So this is the action that we're designing this structure for. That can be resolved into 3 components in these 3 orthogonal axes. So we can resolve it into the X, Y, and Z directions. And we can consider its components. So this force has components in the Y, X, and Z directions. Any force can be resolved into those 3 orthogonal axes in a 3-dimensional space. Okay, so we've got a 3-dimensional bench in a 3-dimensional world with a force coming on which can be resolved into those 3 dimensions, X, Y, and Z. So we can say that all the actions or all the forces in the y direction, which is the one that we looked at initially, so this is a force in the y direction and it has a negative value, and that's counteracted by another force in the y direction in the positive sense. So it's a reaction, but we're going to class it as an action or a force, and all the ones coming down have to balance all the ones going up. If we don't have that, so if the ones coming down are greater than the ones going up, then our structure is going to want to somehow deflect in the direction of the force, so it will accelerate downwards until such time as another force comes up to balance that. If it was in space, for example, if you were designing a space station structure, which you may well be, that would continue to move until some other force came in and acted in the other direction. But for most civil engineering structures, we hope that they're going to be stationary. At some point they may settle, this bench may settle into the ground slightly, but at some point it will reach a state of equilibrium in the vertical direction. So the sum of all the forces or actions in the y direction will add up to 0. Okay, so coming back to our structure again, so let's just tidy this up a bit. We're looking at our cuboid, which is our model of our bench for the purposes of this analysis. As I say, the model is simplified to a cuboid because that's all we need it to be to look at it from this point of view for this exercise. We've looked at forces in the y direction. So actions in the y direction add up to 0. So we've got one equation of static equilibrium. Okay, and that's for forces in this direction have to balance forces in that direction to stop this thing moving down. And if we remember, we said that was our y direction, this is our x direction, and this is our z direction, drawn in isometric view. Okay, so we said that any force acting on this structure could be resolved into those three components in along those three axes. So we need to consider now forces in the x direction. So we could come up with, it could be a wind force, or it could be somebody leaning against our bench, and that is a force or action in the x direction. And in order to resist that, again, we need to have some frictional force or some location device which fixes it to the ground such that that can generate an equal and opposite force coming back in the x direction, which means that this thing is in equilibrium and this structure is not trying to slide or move or accelerate in this direction. Okay, again, under F equals ma, if there's an imbalance, so if the wind load or the person leaning on the bench is not met by a resistance from the ground, friction resistance, or some bolts that bolt it into the ground, which produce an equal and opposite force in the opposite direction, then that thing is going to accelerate in the x direction, positive x direction, if this one is greater. So again, we can come up with another equation which says that the sum of all the actions or forces in the x direction have to add up to 0 for this structure to be in static equilibrium. Okay, so we've now looked at those two directions. Let's just keep on top of where we're going. Let's just put this one up here so we can keep them in alphabetical order. So Fx, the sum of the forces or actions in the x direction, equals 0. And just to complete our system, if we had a force that was acting, say somebody was behind the bench pushing on it in this direction, that would be an action in the z direction, and that would have to be met by an equal and opposite force in the z direction in the opposite sense, in order to stop this thing from trying to, let's say the force was coming from behind pushing forwards, the tendency of the structure would be to want to move in this direction. So our structure would try and slide along the ground in the positive z direction. Okay. Again, for equilibrium, we want to avoid that happening. So we need to satisfy for static equilibrium that all the actions in the z direction add up to a value of 0. Those are our three equations of static equilibrium from the forces. We will come along in the next video to look at 3 more equations of static equilibrium that we can come up with for this structure in a global sense, that will assist us in our understanding of analysis of more detailed components. So at the moment our model is just a global model. We're looking at the global actions on this structure, preventing it from sinking into the ground, so forces in the y direction, or sliding along the ground in the x direction, or sliding forwards in the z direction. And as designers, we need to consider those. It may seem to be a very labor intensive way of designing a park bench, and to be honest it is, because we would simplify it again and use rules of thumb or our just understanding of small structures to come up with a design for a park bench. When you start to get into large structures, complicated structures, big buildings with lots of loads going on, we need to have a system of keeping on top of those and keeping the analysis in check, and have a systematic way of looking at structures. So we may seem to be overcomplicating this park bench, but these are principles which we will use to develop to look at bigger structures, more complicated structures, and their design. Okay, so as I say, next time we will look a bit more at modeling, simplification, assumptions, and we will look at 3 more equations of global stability to give us the full set of 6 equations of the 6 degrees of freedom for static equilibrium. Okay, thank you.